But now I'd like to introduce our next speaker, who is David Murray from MEDITE SMARTPLY. David.
Thank you, Isabel. So over the next 15 minutes or so, I'm going to introduce a new project from MEDITE SMARTPLY called Project Net Zero Home. But first, before I describe the project, I just want to look very briefly at why net zero carbon. Why are we trying to achieve net zero carbon? Well, obviously, the first and most important part of this is global warming. If we have any chance of reaching a maximum temperature gain of 1.5 degrees, it's widely understood by the building industry and professionals who operate in that industry that 100% of buildings must operate at net zero carbon by 2050. Secondly, by 2030, all new buildings must operate at net zero carbon. Now, both of these objectives are looking at operational carbon. However, the bigger challenge, as I see it, is that with nearly 350,000 new homes per year required, which is a combination of Ireland and the UK numbers, the construction process itself must be low carbon. So if you quantify that out a little bit more over the next 27 years up to 2050, you could be looking at 8, 9, 10 million homes that are going to be built. So the materials are a really critical part of that jigsaw puzzle. So as I mentioned, at the moment, there are guidelines, a lot of guidelines around net zero operational carbon, as it's called. And that net zero carbon it looks at the energy efficiency of buildings. So you get a building to be extremely energy efficient, and you add in 100% renewable energy and you net out at net zero carbon. But obviously, the elephant in the room here is embodied carbon. At no point in this so far have we looked at the materials and the processes that go into constructing the building in the first place. You're just looking at the operational carbon that's emitted from the use of the building when it's built. So really, that is a key topic and central to this presentation. So the project itself, the Project Net Zero Home, will look at not just operational carbon, but construction carbon as well, and bringing that right through to the end of life. So looking at a whole life carbon situation, where we'll do a calculation looking at all aspects and all phases of the build, from production and construction through to the use, the operation, and what happens to the building materials at the end of its useful life. So what is Project Net Zero Home? Well, in very simple terms, it's a real-life exemplar new build family house that aims to achieve net zero whole life carbon, as I just mentioned. Really, what the project does is explains the importance of really good design, quality products, and good workmanship on site. It demonstrates modern methods of construction and offsite construction in such a way that showcases low carbon building materials and engineered wood solutions. Throughout the project, we will be launching a series of educational video series, which follows the build sequence as we go through the build. We also have some really neat illustrations, which as-built animations, really, I suppose, which bring the project to life. So the animation that you see here on the right is exactly as the building was designed and built. So it's a really handy and useful visual tool for people to understand what's going on in the project. Following on from that, then we'll bring it a little bit further to make it real, and we have a pretty inspiring 3D virtual tour with key information tags, as they're called, for reference. So you can see the color tags down here and here, which I'll describe in a little bit more detail later on. Really key and fundamental to the success of this project is for MEDITE SMARTPLY to demonstrate the use of our products, and what goes along with that is to provide transparent information and independently verified sustainability criteria. So sustainability for a company that operates in forestry and wood products is absolutely fundamental and critical to our success, and really key for the industry. It's a key topic for the industry at the moment, hence the reason that we're pushing the extremes here by trying to go whole life carbon on the project. There are some other aspects of building a house. When you build tightly in terms of air tightness and insulate, a lot of insulation, you also need to consider the importance of building science, or building physics, as it can be called, as a key design criteria. So we look at that towards the end. And really, you know, a key goal of the project is to validate or eradicate the performance gap. And what I mean is, obviously, the performance gap between design and as-built construction can be pretty horrific in certain cases. So By the end of this project, we will be able to demonstrate that there either is no performance gap, so that the building does perform as it was designed to do, or in the cases where there is a design performance gap, that would be at least we'll be able to validate that and learn from it. And really importantly as well, it proves here that building net zero is not rocket science. It's very complex, obviously, for the number crunchers behind the scene, but really this project aims to demonstrate that it can be done by real people, real builders, real architects. In fact, the architect and builder had no experience in timber frame whatsoever. The builder was a block layer by trade, so very traditional, but it just shows the importance of working as a team and using people's initiative and people that want to learn new methods of building. So it can be done by anybody is one of the key learnings from the project. So having looked at what the project is, let's look at what the project is not. So it's not a box. A common misconception, I suppose, of passive house design, in that you're very limited in your design flair, and it has to be a very boring box, either square or rectangular. So what the architect has done in this case is quite clever, taking the simplicity of a box design, but actually having 3 boxes, or 4 if you count the garage, and putting them at different heights and different and set off from each other in a kind of a vernacular style, which was quite impressive. It was picked up by an example here from the, it's an extract from the draft Carlow County Development Plan in Ireland 2022 to 2028, chapter 13 Rural Design Guide, and there's a photograph included in that design guide. And the language that they described it as was a contemporary, or the architecture was described as contemporary language based on traditional elements and materials. So it's nice for the architect to get recognition for that. From there, we took the design from the architect, the detailed drawings and so on, and the timber frame manufacturer's drawings, and created a 3D animation model that I mentioned earlier on. So we'll have a look at that shortly. And finally, you can see it's not just drawings and designs, it's an actual house. It actually did get, it is being built at the moment. Here it is at the practical stage of timber frame completion. So next we're going to take a quick look at the steps to achieving net zero carbon building in practice. This is a useful guide taken from the UK Green Building Council's Net Zero Carbon Buildings Framework. And it sets out very clearly a kind of a hierarchy graph of achieving net zero in 2 stages: construction and operational energy. And I'm going to start with operational energy because that's the part that's covered in Part L of the building regulations and is very clear to everyone. And as you work down through the table, you can see the key word here is to reduce. Reduce your construction impacts, you reduce your operational energy use, and then you reduce your fossil emissions by increasing the use of renewable energy supply on site. And then you you offset any remaining carbon. And the key to this is all about, as I said, Part L of the building regulations is all about reducing operational energy use, is linked to energy efficiency of the building fabric, and then using renewable energy supply, such as either on-site or off-site renewables. And then, as I said, any remaining carbon burnt can be offset then at the end. And if we go back then to the elephant in the room, and I suppose that's the construction stage here, is this part here is to reduce the construction impacts of the materials and construction processes by undertaking a whole life carbon assessment, which looks at the embodied carbon impacts of the product and the construction stages, and these can be measured and offset at the practical completion stage. So following down through, D stands for design. So these 2 here should already be included in the operational, so they're designed in at the operational stage. And then at the end of this, you can you can offset any remaining carbon at the end of the construction stage. So that's at a very quick overview. There's one remaining part here, which I'll describe in a second, but just a very useful definition of both of those terms. Net zero carbon in construction means when the amount of carbon emissions associated with a building's product and construction stages up to a practical completion is 0 or negative, through the use of offsets or the net export of on-site renewable energy. And then for operational energy, a definition includes when the amount of carbon emissions associated with the building's operational energy on an annual basis is 0 or negative. A net zero carbon building is highly energy efficient and powered from on-site or off-site renewable energy sources, with any remaining carbon balance offset. So as I mentioned, the third part of this is again going back to the elephant in the room is net zero whole life carbon, which is in development at the moment and is really going to be a focus of the project Net Zero Home. How you get to that stage is you start to really scrutinize the data behind the products. This is an example of an EPD, or an environmental product declaration from MEDITE Vent product, which declares modules A, which is cradle to gate and cradle to practical completion on site. It also declares module C, which is cradle to gate, cradle to grave, and then the option of declaring module D, which we've done in this case, and that is the cradle to grave, including benefits and loads beyond the system boundaries. So this is again where it gets complicated, and it's not required yet. But module D is all about the reuse, recovery, and recycling potential of those products at the end of the building's useful life. So in practice, how will we achieve it? Okay, let's go through a list here. So, you know, obviously I'm starting with low embodied carbon materials because I work for a forestry company and wood products company. So that's obviously key to this, the topic of this presentation. The next 6 on the list are all to do with the building fabric and reducing the operational energy. So by creating a very energy efficient thermal envelope or building fabric, this is easily achieved. Things like the orientation of the building, both building and windows, the insulation should be continuous and balanced. In other words, you know, no point in having thick insulation in one part and thin in another part. The airtightness will be exceptional. I'll come back to that later on. The thermal bridging will be completely eliminated, and this will be verified by independent calculation. The building will have high performance windows, so triple glazing, and again balanced. So, you know, balancing the amount of glazing facing south to minimize overheating, for example, and minimizing to the north where you're not getting any solar benefit from that. And the final part of this is mechanical ventilation. When you're operating and building a building at such exceptional air tightness levels, you do need mechanical ventilation. And obviously, if you have residual heat in the building, well, you might as well recover that to heat the incoming air coming in. So by doing that, the house will be hopefully be a certified passive house. However, that's still not in compliance with the Irish Building Regulations Part L. So I've added in here as well that the building aims to achieve A1 BER, or building energy rating. And this would be quite unique, I believe, if it happens, because most buildings end up at A2, but to get A1 without the use of photovoltaic panels is quite unique. So to achieve the A1, you would need to put in an efficient electric heating system such as air to water heat pump, which obviously gives you a heating system and domestic hot water. And then obviously you go shopping and find as many energy efficient lighting and appliances as possible when you're running the home. The next stage, as I said, I left it out because renewable generation from solar PV and storage is a nice to have, but if you can get to A1 without it, so much the better. It may be a useful and a nice add-on to get to a net zero positive energy home. But I think it's an important, again, consideration to look at the overall carbon impact of doing this. And what is the benefit of solar PV versus the carbon cost to the environment of doing that, I think will be part of the project. So again, all of these things we're looking at here from 2 down to number 10 is all to do with operational net zero. And as I mentioned earlier on, the key ones for this project, the key difference to this project from other projects is the use of low embodied carbon materials. So lots and lots of wood products and engineered wood products, which will form part of the whole life carbon assessment. And then if there is any residual carbon to be offset at the end, that would be done through recognized and verified systems. So now I'm just going to show a very brief overview of the fabric first design. So as I mentioned earlier on, the importance of designing and constructing a highly energy efficient building, you really need to look at the fabric first principles here. And this goes right the way from the ground up to the roof. So what you can see here is the building doesn't have a traditional strip foundation. It has an insulated raft foundation, which is highly insulated to minimize and eliminate that thermal bridge from the ground floor into the ground. So you can see lots of insulation. And actually, one of the benefits of this is we estimate that there will be approximately 43% less concrete required than a traditional strip foundation. As I mentioned earlier on, to comply with Part L of the building regulations, you do need a heating system, contrary to popular belief, but that heating system is completely different to a standard house in that it operates at very low energy. So working from the ground up, then you can see here the fixing of the sole plate to the slab. but it is not any ordinary sole plate. This is a thermally broken sole plate. So it's a double sole plate with insulation between, upon which the closed timber frame panels then sit and get fixed down onto the sole plate. So again, you can see this is exactly as the sequence as it was built on site. The closed panels themselves are formed with I-joists construction with SMARTPLY PROPASSIV. The green board there you can see on the inside is the airtight layer and the vapor control layer. And the outside board then is a product called MEDITE Vent, which is a diffusion open fiber board. So you have a closed panel to insulate. At first floor level, then a product called Strong Deck, which is an OSB 4 product. So very thick and very strong. At the floor zone, it's critical to minimize thermal bridging at this critical junction here at the floor zone, and also to make sure that is extremely airtight. So the detailing around that is extremely important, and that will be detailed fully throughout the build. There are 3 different roof types in the building. So a flat roof, 2 pitched roofs insulated at ceiling level, and a pitched roof insulated at roof level. And you can see the trusses being applied on the pitched roofs. So the pitched roof here, as you can see, has a raised heel truss, and this allows a very significant amount of insulation to be added at ceiling level. Here we've used I-joists again here at ceiling level, so we're going to insulate this along the roof line as opposed to ceiling level. MEDITE vent across to provide structural racking support, insulated on top to minimize any thermal bridging that may come through the roof. And finally, the addition of the roofing membrane, roofing battens, and so on. So next, we're going to take a look inside the house using the 3D virtual tour. This is a really handy visual tour tool that you can literally take a walk through of the house, going through the various rooms, looking at the products on the walls and on the floors, moving upstairs, lots and lots of timber and engineered wood products you can see, obviously. Again, lots and lots of timber. These tags here illustrate that there is product information. So if I click on that, it's the technical data sheet for the OSB product that was used on the floor, a product called SMARTPLY Strong Deck, which is an OSB 4 product. And if I go back into the model then again and go back downstairs, I'll just show a couple more examples of tags in the kitchen living area. So for example, on the outside here, we have the MEDITE Vent data sheet, environmental product declaration and EPD. And if you click on that, then you can get all of the various environmental information. That's the information I showed earlier on in the presentation. Going back into the model then, again, walking through here, this is the SMARTPLY PROPASSIV airtight OSB documentation. This is the installation guide. This is the declaration of performance for that particular product. And down here in the corner, you can see examples of very short video clips that we put together just to demonstrate the various connections of the video to explain how the whole building comes together. And similarly over here on the other side, more short video clips, this one explaining how the actual sole plate connection is detailed and connected and made airtight. So it's a really fun interactive tool to use. This photograph here is an example of the meticulous level of detailing that went into the house from an airtightness point of view. This is an airtightness quality control station where the contractors marked down or noted anywhere that penetrations were made in the airtight layer. So the plumber, the contractor, the electrician and so on, all noted where they made penetrations in the airtight layer so that they could be found and made airtight before the building was closed in. So again, it's a very useful tool. We'll be adding to this as the project develops with lots and lots of information, lots of video clips, and hopefully this is a useful tool for people to learn how to build a net zero home. So having looked at some of the products in detail in the 3D virtual tour, I wanted to focus in on 3 areas which are absolutely critical to the success of building a net zero carbon home in terms of the product use. As I mentioned earlier on, a product called SMARTPLY PROPASSIV is used as the main air tightness strategy on all walls and ceilings. And that pretty much guaranteed air tightness. And we knew this because on the photo on the left here, you can see the board, which was tested many years ago in a test rig in Germany, tested to 2000 pascals of pressure, both positive and negative pressure. And you can see here 2 sheets of the board with a tape joint in between, demonstrating that the board is extremely airtight to put it mildly. You can see here, even at 2000 pascals, no air was leaking through, and the integrity of the joint remained in place. So bringing that through to a site where you are testing here with the blower door, doing the blower door test, you can see the board in the background here. I kind of renamed this as a blower window test because the Gavin O'Shea, the Greenbuild, who was the air tightness assessor, I think it was the first time he had used such a small fan, because the air leakage in the building was so small. You only need a very small fan to get your pressure difference between inside and outside of 50 pascals. So the result here, which was an exceptional air tightness result, was 0.08 air changes, an N50 value there, which is fed into the Passive House planning package. I think it's also important to note here that the permeability, the Q50 value, is also extremely low and very, very close to the N50 value of 0.081. This is measured in a different way, looking at surface, exposed surface areas. So the fact that both of those numbers are very close is a very good indication of the performance of the building. Looking then at thermal bridging, this is just one example, probably the worst case example of a potential thermal bridge in the house. I say potential because it was eliminated. So here you can see inside the house where you have a pitched roof intersecting with a flat ceiling here. This is the I-joist coming down onto a steel beam, and this is the raised heel truss resting on a second steel beam. And you can see it here down in the bottom left. As it was being built, you have 2 steel beams, and obviously there's a lot of load here, so you did need the steel beams in here. However, with this meticulous design detailing and absolutely brilliant craftsmanship and workmanship on site by the timber frame erection team, they designed this junction and encased the steel beams completely in insulation. And here is the thermal bridge assessment, which shows the plane element U values of 0.09, and a psi value has been calculated at 0. So all heat loss is completely eliminated from this critical junction between the 2 roofs. And finally, then, we, as I mentioned earlier on, the importance of building science is really critical when you're designing at this level of air tightness. It's important to understand the implications that can have. So really, building science should be a fundamental part of good building design. So what we did here at the construction stage of the timber frame is we inserted a number of moisture sensors. So these will measure temperature, humidity, and dew point. And we put sensors in at various sections throughout the wall. You can see here, this is obviously a cross-section of the wall, an insulated surface cavity with the PROPASSIV board on the inside, which is the airtight and vapor control layer, and then an I-joist with MEDITE vent on the outside and a ventilated cavity outside of that. So the position of the sensors are before the PROPASSIV, after the PROPASSIV, in the middle of the insulation, which is this one here. Number 4 then, which is on the inside of the MEDITE vent board, and number 5, which is this one here, which is outside in the cavity, which will be sealed up behind this breather membrane. You can see here an airtight grommet to make sure that the building airtightness remain intact. But this will give us, hopefully help us to validate the building science data from the WUFI model that was done at the design stage, and this will be in situ permanently. So we will have validation of that we'll probably look at it over a 3, 4, or 5 year period, but it will be in the building constantly. So I think it's a very useful tool. And this helps us as manufacturers to work with specifiers to give real life as built data on our products to demonstrate that it does actually perform as it was designed to do. So that's it from me. Thank you for your attention this morning, and I would welcome any questions in the feedback session. If you would like more information on the project itself, you please visit the website. I think it should be all live by now, but you can see the project is called Project Net Zero Home. It will be putting it on Instagram, LinkedIn, Facebook, etc., and obviously all through our website. So your first protocol, please, if you have any questions or you are interested in the project, is to log on to our website, mdfosb.com.